All
Yes.
right, finally. Okay, so Christine, this is the first class. This is an introductory class in the ICE methodology, and it's primarily for our students in Finland who are just starting the program. And so I'm going to talk a little bit about the history of how this started. And then I'm going to give an example. And the example of the methodology that I use is the return to flight of Space Shuttle STS-114, which was my mission. And so these are some of our partnering organizations. Right now, we have the Astronaut Memorial Foundation, some of our newer ones, Higher Orbits, the Mentor Project, the Council for International Education Exchange, and others. And you see several of the universities that we've worked with in the past. Okay, for the students, I was training in Russia when the STS-107 accident occurred on February 1st in 2003. This shows you the launch of that mission in January 16th. And what the people on the ground saw was a large piece of foam breaking away from the external tank. If you look on the left, if you look on the right, it shows another view of that foam, and it's pretty obvious it strikes the bottom of the vehicle. Not quite sure if it hit the white section, which are the shuttle tiles, or if it hit the dark section, which is the wing leading edge. What's important to note is that the people on the ground, the really smart engineers and program managers that were in charge of this mission, when they viewed that video and they ran their calculations, excuse me, they determined that it was not a problem. And what we all know now is that during entry on February 1st through the Earth's atmosphere, um, the vehicle broke up and we lost the vehicle and the crew. And so we spent, and so one of the main questions I had when this happened was, I was in Russia, was how could these really smart people make such a bad decision? And so even really good engineers, if they do not think critically, if you don't have a psychologically safe environment, what happens is you can't raise your hand, you can't speak up. And so this happened. And so we spent the next 2 years, 2.5 years, trying to understand the cause of the accident. We literally had and figuratively had to pick up the pieces. We had about 85,000 pieces spread across southeast Texas. We had hundreds and thousands of folks combing the area in these rural area of Texas, picking up the pieces, putting them together, and now we're trying to do that forensic analysis, trying to put the pieces together to figure out what caused the problem. And so this really began the origin of the EPIC Challenge program. We developed an innovative conceptual engineering design methodology, or ICE, and I'll talk about that. We started right after the accident, putting teams of people together to understand what caused the problem. We then created a small team to determine a repair technique on how to fix the wing leading edge. And then after I came back from my mission, basically developed this methodology and this program with four other faculty from Georgia Tech, Penn State, and MIT. And we taught it for young NASA engineers. So in 2008 and 8, we developed this methodology. We went to Penn State, and in 1 week's time, we took 30 young NASA engineers and we ran them through this program. And the problem that we picked was a challenge that even NASA was struggling with at that time. It was basically designing a capsule to land safely on land. As you know, Space Shuttle lands on land, but it's a winged vehicle, and all of the United States' space capsules land in the ocean. Okay, so we went to Penn State, we posed this problem. We created an environment where the researchers were immersed in the problem. They could then use the facility there to use computer programming to kind of analyze the problem and build some of their ideas. So they were able to prototype some of their ideas. We ended up with dozens of ideas from that 1 week training session. And we selected only one of those ideas, which you see here, which was an airbag concept. And we basically took that one concept and we went to a group of students. We had an MIT master's degree student, Sydney Doe, and we had 8 MIT and Penn State undergraduates basically work with Sydney for about 2 years on and off, and they basically matured their idea, which was an airbag concept, and they ran a series of tests, both subscale and full-scale tests, and they basically created, they proved that their concept would work, that it would not only enable the astronauts to land safely without injury, but it also would reduce mass by about 36%, and it would increase the habitable volume. So what this did was this proved that the concept worked, this idea and this methodology works, the idea that we could take some of these epic challenges, go to students like yourself, and have students around the world help NASA and industry try to solve these really big challenges. So these are some of the themes of the ICE methodology. The first one is the human mind, use it. We try to teach the students to think creatively, basically use their mind, not only rely on computers. We want to teach them to work together in a team and not be arrogant, okay, to accept everyone's input and factor that in when we're trying to solve our problems. The other theme is understanding the mechanisms of failure, all right? As we go through this process, you as a member of a team will have lots of ideas. You're going to share those ideas. And what I encourage you to do is basically look at every idea objectively, even your own ideas. Critically assess and think about all the different ways your ideas could fail. Failure is very important in this process. And so you see here on the right, failure is not an option. In this program, it's a requirement. And we're going to teach you as students how to design experiments so that you can fail smart, fast, small, cheap, early, and often. We want you to fail intelligently. We want to teach you how to run experiments in the laboratory so that you can close the knowledge gaps and you can gain as much information as possible, okay, in order to understand the problem. You're going to be working together on teams, okay? And so we're going to teach you how to work together in teams, how to share that information. We're going to teach you a little bit about systems engineering and what systems engineering is. And so the next theme is panning out and zooming in. Good systems engineers have to understand the big picture that they're trying to solve. And what you are going to be doing as part of your program is you're going to be looking at one small aspect of a much larger problem. And so as you're working on your piece of that problem, you have to understand how every change you make to your design, how that affects the larger system. Okay, we're going to teach you a little bit about creativity and the need for taking time and relaxing and giving your ideas time to incubate. When you come up with new ideas, share them with your classmates, your teammates. Think about the ways they could fail and think about ways that you can improve those ideas. And the last theme is that really everyone is creative, and we're going to teach you techniques to enhance that creativity, that individual creativity, but more importantly, how do you work together so that your team is a high-performing team and you think creatively as a team? That collective intelligence, that collective creativity. Does anyone have any questions? Okay. So what I'm going to do now is show you how I was taught as an engineer and a researcher. How do you create knowledge? How do you create new knowledge? Okay, you look, as engineers and scientists, we look at the physical world, we see something, and we try to create a mathematical or an analytical model that represents what we are seeing in the laboratory, right? Or what we are seeing in nature. Then we go in the laboratory and we conduct an experiment. And then we're constantly evaluating how well our analysis or our understanding of the physics of the problem actually holds true. The assumptions that we make, do they hold up, and can we predict what's happening in the laboratory? And more often than not, this doesn't happen. Results don't correlate well. And so that's why you have this double-ended arrow here. You're constantly going back and forth, trying to understand whether or not your analysis is accurate enough, whether or not your experiment is set up correctly, and there are some errors in your experiment. Once you are able to actually predict what's happening in the laboratory, to understand the physics of the problem, you vary lots of parameters, and I encourage everyone to test the failure and understanding if you can actually predict when that failure happens. When that happens and your analysis is then validated or verified, you can then use the computer and your numerical or analytical understanding of the problem to now look at lots of different ideas, lots of different variations of ideas, and you analyze them numerically, right? And you try to come up with an optimum design. You're constantly looking to improve your design. Once you come up with what you believe is an optimum design, then you go ahead and you test that design by an experiment. And you do this because more often than not, as you're moving through this design space, varying parameters, you may have exceeded an, an assumption or a requirement. Okay, and your analysis might not hold. And so more often than not, you will find that that happens, and then you go back to your analysis and add that constraint or that improved understanding of the physics of the problem. Okay. And I'll give you an example of, of how to do this. This is an example. We use what's called the building block approach. And so we start in the laboratory with very simple experiments. This was an idea for a honeycomb sandwich structure, which was going to be used in a cryogenic tank, a reusable cryogenic tank for a single station orbit vehicle. This had never been done before, has never been done. See the honeycomb right here? The idea was to evacuate the honeycomb and use the honeycomb structure as also a very good structure and also a very good thermal insulator. So when we put our cryogenic propellant inside the tank, um, it does not boil off as readily. Okay, the problem is when you're trying to design a hydrogen tank, hydrogen is a very small molecule and it's very easy for this system to leak. And so if you have a leak in this cryogenic tank, it could fail. It could fail because liquid leaks into the honeycomb. When you launch the vehicle, that liquid heats up, it expands very rapidly, it could blow the honeycomb apart. So what we did was we designed lots of small experiments and we stepped through this process, gradually building up, understanding combined loading that this structure would have to take in this cryogenic tank before we actually build the final design. Now, what happened was, and this we call intelligent fast failure, and we'll teach you how to do this as part of the ICE methodology. But if you fail to do this, this is a real program, okay? This was a single station orbit vehicle called the X-33 vehicle. It was contracted by Lockheed to NASA to build a single station orbit prototype. It would be a demonstrator. What happened was The program built the very large honeycomb tank without doing without using that building block approach. And what happened was it failed in final design with a full-scale test. And because of that, it totally canceled the entire program. Because this failure happened late in the program, it cost a lot of money up to that point to actually build this concept. And when they failed, they had no backup. And so what I'm telling you is by not doing that building block approach, entire programs could get canceled. So this is the ICE methodology. Okay, you're starting it just now. You're just starting to form teams. Very early on, we will teach you how to form teams, how to work together as a team, which is very important. Okay, and then we're going to teach you how to immerse yourself in whatever problem you're trying to solve. You have to work together as effectively as possible as a team. Okay, and so what you have to do is you have to quickly understand everything you possibly can about the problem. These are very large, complex problems, so you need to divide and conquer. You need to split up, and different people on the team look at different aspects of the problem. Then you have to come together as a team and share that information. Okay, and we'll show you how to do that. The next phase, as you're stepping through this understanding of this problem as a team, is now once you understand or think you understand the problem, now you have to try to come up with ways to solve the problem. And so we're going to teach you how to do that. And there are several techniques we teach you working together as a team, maybe brainstorming, biologically inspired design. We'll teach you different techniques for expanding and enhancing your creative approach to solving the problem. Okay, and then you'll end up with lots of ideas, right? So now you as a team have to use logic and have to use analysis and testing in order to evaluate those ideas. And we call this the rapid concept development phase. And so as you're going into the laboratory as a team, building experiments, I want you to teach you how to do this as quickly as possible, okay? Because we need you to understand and to learn as quickly as possible. And so we go through these different phases, and the whole reason for this, and the whole reason we're focusing on what we call the conceptual design phase, is because this is where most companies fail. This is where NASA fails over and over again. What happens is we down select to an idea that we think is a good idea without fully understanding that concept, without evaluating all the different ways it could fail. And so we go into a development program like you saw with the full-scale tank with one idea. They honed in on a evacuated honeycomb core sandwich panel. And then what happened was late in the design cycle, well, as they're developing and they actually manufacture a full-scale design, they fail. And they have no backup, and they have to start from scratch. This is what causes lots of programs to be delayed by years in some cases, and for costs to rise exponentially. So what we're going to do is show this ICE methodology, if you will, and applying it to the return to flight wing leading edge problem. Okay, so what we're going to do right now is we're going to go through these steps. We're going to go through the problem definition of what caused the accident and the problem that we are going to solve, how to repair a wing leading edge. We're going to show you a little bit about the team we developed, about some of the techniques we used, and so this is the problem, okay? It's a large piece of foam hits the vehicle and damages the vehicle. We think, but we're not sure, right? So now NASA has to understand, did that piece of foam, that large piece of foam, really cause the damage which caused the accident and the loss of the Columbia crew, right? So when we're looking at this problem, we have to look at all the different constraints on the problem, okay? Once we understand what caused the problem, we have to understand if we're going to fix the problem, if we're going to repair the wing leading edge, we have to understand the temperature limits. How hot does the wing leading edge get at its hottest location? Okay, what happens if we just damage the coating slightly? Will that cause the entire hole to grow, a hole to grow on the wing leading edge? Hot gases go in, and will that cause failure of the vehicle? We have to be, we are often constrained by cost. NASA doesn't have a tremendous amount of money. We're constrained by time. We want to be able to solve this problem as quickly as possible. We also have political pressure. If we fail to solve the problem and the next crew that flies, if we lose the next crew, will the entire space program in the United States be canceled? Okay. We have to think of all our techniques that we're looking at to fix the vehicle. How are we going to be able to operate those solutions? In other words, if we're trying to fix a wing leading edge on orbit, we have to think about the astronaut in the spacesuit, right? Constrained by the pressure inside the spacesuit, the dexterity of the gloves, things like that. And once we come up with an idea, how are we going to validate that idea and make sure that the people on the ground, NASA, and the safety people are going to certify that we can actually use this in space? Okay. Some of the things we also want to think about as we're looking at new ideas, we want to look at contradictions in the problem, because usually if there's a contradiction, this is usually an opportunity for a designer to come up with an enhanced or a breakthrough idea to solve the problem. For instance, in the wing leading edge, thickening the wing leading edge to make it tougher will also cause the external surface to be hotter and might exceed the temperature limits, okay? So we're going to look at some of these contradictions. Once again, we want you to make sure that we have to look at every problem as if it's a multidisciplinary problem and part of a much larger system. Okay. So every problem's a multidisciplinary problem. We want to identify all the potential constraints, look at all the different ways it could fail, look at the contradictions within the problem to see if there are opportunities. So for the wing leading edge, for the Space Shuttle STS-107 Columbia accident, we want to pan out and look at this problem, right? So this is what NASA did. Basically, right away, they started looking at what was the root cause of the problem. A large piece of foam came from the external tank, the bipod ramp, and it struck the vehicle on the lower surface, either on the wing leading edge or on the fragile thermal protection system tiles. Taking a look at that just gives you some idea of the size of the debris. The piece of foam could have been as large as 2 pounds. It had the density of about styrofoam, and it was traveling at about 545 miles an hour. And and they made these calculations based on the video that we received. Okay, they analyzed this video and they determined that the relative velocity of impact was about 545 miles an hour. Okay. So what you saw, the people in the hangar at Kennedy Space Center, they started putting the pieces together, the debris that they found on the ground. These are the pieces of reinforced carbon-carbon wing leading edge panels 5 to 10 that were put together at the Cape. It's from the port wing leading edge. And you notice that collected lots of the pieces, but some of the pieces were missing, right? We think a lot of the damage based on the video footage, it appeared that it struck probably between panels 8 and 10. When they started looking at the debris of these panels, you notice the inside surface is coated with a silvery coating, right? What we believe happened was the panel was damaged. Either a large hole appeared or a crack grew. Hot gases ingressed the cavity of the wing leading edge, and it was so hot it vaporized the metallic structure of the vehicle. That vaporized metal then deposited on the inside surface of the wing leading edge. Now, this is what the engineers on the ground believe. It really appears that a large piece of foam caused the damage. And so in order to understand if that was true, they developed a full-scale test, all right? And the way they originally decided to do this test, it was going to be a full-scale test, a very large pressurized railgun shooting a large piece of foam at a full-scale section of the wing leading edge. How they originally planned to run this test, had they done it the way they originally planned, it would have been a very dumb, expensive test. They weren't planning on doing any analysis to understand if they could predict what was going to happen before this test. And they did not have enough instrumentation on the test element in order to basically correlate their analytical predictions with the test. If we had allowed the Columbia Accident Investigation Team, if we had allowed the engineers to run this test, we would not have been able to get much information from that test. Instead, we told them to follow the methodology we showed previously, basically conducting intelligent experiments and using a building block approach. We collected the subject matter experts and
Charlie, could I have a question here?
yes, let's go ahead. We'll stop this. Go ahead.
I just had one question, not the students, but I was just thinking, so do I understand this right? So is it what you're trying to say, that if they would have run the test, they would just have seen that, okay, there's going to be a hole, but they would have not understand why this hole is there?
Exactly. And look how long it took them to build that full-scale test. They would have shot this large piece of foam at all these prescribed parameters, you know, at this angle, at this speed. They would have struck the large full-scale replica of the wing, and they would have determined, was there damage, was there not damage. But then they would not have any useful information. They would not have an analytical model that was validated so that they could reuse and vary parameters, just like we showed in that analysis test design loop, right? Once your analysis is validated, now you could use that analysis and look at different angles, different size pieces of foam and shapes of pieces of foam, and then you could actually predict what would happen in any of those cases, right? And
Yeah,
so
because
go
yeah,
ahead,
because
Anna.
they would have to like put every time there a new wing, a leading edge, and a new angle to, if they want to do it that way, right? So
Exactly. So, as an engineer, as a research engineer, especially me watching them proceed like this, I said, no, you have to stop this. This is now not how research engineers and real engineers solve this problem. It would have given them it would have told the program office, hey, we understand what the problem is, but it would not have helped us as far as proceeding with the program and predicting what size pieces of foam would be okay. You know, when would we draw the limit? So that's exactly right, Anna. And so if we would have just let them run this, but now we basically instrumented this wing leading edge with the full field photogrammetry system inside the wing. So now we could look at millions of points inside of that wing leading edge. We can understand how it's going to deform, right? And we have that test results that we can now compare with our analytical results. Okay? No, that's a very, very good question. Does that answer your question, Anna?
Yes, thank you.
Okay. And so, what did we do? We went to the really good researchers at NASA Langley, at Glenn Research Center, and our friends in Boeing. And we basically now, what you see is a building block approach. We're looking at modeling the foam. We're looking at conducting tests of just small pieces of foam. Now we could run these tests. This is what I call smart, fast, small, cheap, early, and often. We can run hundreds of these tests inexpensively until we understand and we can predict the physics of how that foam is actually going to fail, right? And so now you see we have good working models predicting how the foam fails. Then we proceed to conduct tests of that foam impacting material, small coupon specimens of the wing leading edge made out of reinforced carbon-carbon, right? And so now you see two tests at two different velocities. You see in one case, there's no damage and the specimen survives. The other case, there's lots of damage to the foam and also the target material, which is the carbon-carbon material, right? Now we feel like we understand the physics of not only the foam, but also the target material. Now we can use those analytical models, and this is what the scientists did, to predict what would happen. So this is showing you an impact of foam to that full-scale wing leading edge that the analysts were able to predict prior to actually running the test, right? So now when we run the test, right, and this is a full-scale test, so you see what the folks predicted analytically was actually what happened. You know, when you look at what they predicted, you almost see a 14-inch by 14-inch rectangular section almost coming away. And then when you look at the actual test, so you see it's very good correlation with the experiment. So now continuing to do small tests and some of these large tests will now be able to develop, and we had developed a very precise way for predicting failure, right? And so now we pan back out. If we look at, that's just an example of using that building block approach and that method for constructing knowledge, going to the laboratory, conducting experiments. Now now we understand what caused the problem. We know it was the foam. Now we have to figure out a strategy, and this is what the folks at Mission Control and at NASA had to develop. This is almost every NASA center. We have people working on this problem. How do you develop a strategy to make sure that we won't have a problem the next time we fly, or if we have a problem, we can keep the crew safe? So the first thing we have to understand is what's causing the foam to come off. We want to be able to inspect the vehicle. After we launch the vehicle, we want to be able to inspect it this time. Maybe put detectors on the vehicle to understand if a piece of foam hits someplace critical on the vehicle. And so this is what I call a multi-pronged approach to ensuring that we could fly safe. So we're looking at ways to minimize or eliminate the debris source. We're looking at ways to toughen the vehicle. We're developing an on-orbit repair technique. And if all else fails, right, if we have a large hole and we can't fix it, we're using the International Space Station as a safe haven. That means we're going to take the crew The crew is going to dock with space station. Crew's going to get off, and we're going to rescue that crew with another vehicle. We're going to fly another vehicle in time to bring that crew home safe. Okay. The other thing we have to do as we're looking at all the different teams that we're forming to solve this problem, we have to understand the big picture. Remember, I said we have to pan out. You have lots of teams working on this problem. We have an inspection team wondering, how do we build cameras to inspect the vehicle to determine damage? We have an impact team, a threshold team that has to understand how small damage how small, what's the smallest damage we can incur that will be critical? And we have to make sure, right? So we have to work together with this team to make sure that whatever instruments we design here, they can see this damage. Otherwise, we're flying blind. We think we're safe and we're not safe. So all these different teams have to work together. Information was from one team has to be passed to the other team. They have to be working very closely. Now, what I will tell you is when NASA first started looking at this problem, these teams were totally independent. They were not communicating with the other teams. And so as you form your teams to work on whatever problem you're working on, you have to make sure that you have a plan of communication. And we'll talk about that. Okay, now, once you understand the big picture, let's zoom in on a particular problem. And the problem we're going to zoom in on as an example problem is really the wing leading edge and fixing that large hole in the wing leading edge. So we're going to look at, one of the first things we do is understand the problem, dive into and understand everything we can about the wing leading edge, the material, look at other ways that people have tried to fix structures in space, and look at analogous problems. And once again, I'm just going to emphasize you have to be critical of your own ideas. All right? So right now we're trying to understand all the damage that could have possibly happened to the wing leading edge in the past, and how did that damage progress as the vehicle entered the Earth's atmosphere. So we go back and we look at all the other examples when we had coating loss, when we had debris hit the wing leading edge, what damage happened, and how did that vehicle react? How did it respond to that damage during entry? Trying to understand everything we possibly can about how a damaged piece of reinforced carbon-carbon material, the material that makes up the wing leading edge, how that's going to behave. So the first thing we have to do is we have to bring into our team the material scientists, right? The people that understand how this material was made. And when you look at this material under a microscope, it's a system unto itself. It's composed of carbon fibers. It's composed of a carbon matrix. The entire three layers of that material on inside and outside surface were what we call conversion coated to silicon carbide, right? So silicon was basically packed on the outside. It was heated, and it caused the chemical reaction and created this silicon carbide coating, right? What happens now is you have two different materials. They have micro cracks, so they had to figure out how to protect this very fragile carbon material so it wouldn't burn up as it goes through the atmosphere. And oxygen can now penetrate it. And if you add oxygen and heat, this material would just burn up. So the only thing protecting that material was this very thin, brittle coating. So you have to understand everything about it, everything that was protecting that material from burning up, in order to now, if you have a crack in this material, if you have a hole in this material, how could you possibly fix it? This material is a special material. It basically gets stronger at 3,000 degrees than at room temperature. But you have to understand how this material behaves. The other thing you have to understand about this problem is how this material heats up during Earth entry. This is an analysis by a friend of mine, Pete Naffo, who's an aerothermodynamicist, was at NASA, an expert. And when you look at a flow, he looked at several different size holes in the wing leading edge, and he looked at flow coming in at an angle. And what you see as the flow strikes the downstream lip of that hole, the heating there is very high. And so what this means is if the flow is at an angle to the vehicle, you have much higher heating in the downstream lip. This will determine how this hole grows, how fast it grows, and so it gives us some idea of the limitations or what size hole could potentially cause critical damage. And so what we learned from that was that the way we had been testing this material, if you look on the bottom, was 90 degrees to the flow. Okay, we thought that was the worst case. Once we learned that flow at an angle was a much worse case, we started to change the way we tested, right? So we have small coupons of this material. We're now damaging those small coupons with slits, with impact damage, and we're trying to understand how that damaged material will now react and respond after 10 to 15 minutes in a very high temperature flow. Here the flow is from the bottom up, and you notice a small slit grows, and you notice that the downstream lip, since the flow is from the bottom to the top, the downstream lip here gets much hotter, and so instead of growing symmetrically, it grows like a wedge. So what this meant was that this analysis and this phenomenon that Pete Naffo determined using computational fluid dynamics, we now go in the laboratory and we now understand that this is a real phenomenon and we have to change the way we test, right? We also need to understand all the different anomalies within this material. You know, there are voids in the surface, there are delaminations. What happens if you have a crack? What happens if you have coating loss? One of the things we did was we looked at ways that we could possibly repair this, right? So we looked up, we have a question?
Could I have another one?
Yes.
Yeah, I realized like all these years we talk about this, I have never like asked this question that you know, because they did, the problem actually happened when they were coming back, right, to re-entry. So it's like really, I'm thinking now, like how come we didn't notice anything while they were going up? Because the hole was already there.
Right, the hole was there. And so, and that's a very good question, Anna. And this crew, this poor crew of SDS 107, they did not have the means to basically inspect to see if there was a hole there. Okay. Now, people on the ground said maybe we could use U.S. Air Force assets, and basically they would be good enough to determine we could image the vehicle and we could determine if there was any damage. But the people on the ground asked to make that request to the Air Force, and people at NASA said no, they denied that request. And there's a whole lot of other reasons why that happened, and it was a very bad decision.
But was it so that they were already in a when this particular problem happened? Was it because of temperature or because of just the angle of the spacecraft during launch? Or
No, it was just probability. It was just probability, Anna. What we found out after this was that pieces of foam had been coming off ever since the first space shuttle flight, right? And so we were constantly losing these large pieces of foam. We were continuing to fly, and we were seeing damage to the vehicle, but the vehicle was surviving, right? And we had become arrogant. We thought we understood this problem. And so this is, sociologist Diane Vaughan calls this normalization of deviance, right? And that's why we need these behavioral scientists and these sociologists to understand why we made these bad decisions. We see anomalous behavior, right? And it's something that wasn't supposed to happen. We see damage to the vehicle survives. Why don't we stop flying? Right? We continued to fly. We continued to convince ourselves that we understood a problem we really didn't understand. So, SDS-107, the crew was in orbit. They had damage to their wing. They could not inspect it. We prevented people from the ground and using Air Force assets, right, classified assets, to see if there was damage. The other factor was we had no robotic arm on that vehicle. The space shuttle flies with a robotic arm in the payload bay. Almost every flight has one. This one particular flight, because it was going to a totally different orbit, right? It had to save weight, so they had to take off that robotic arm. Otherwise, we could have used that robotic arm to go outside and inspect the vehicle, and we would have seen the damage. The other thing which caused this crew to be so, that was so unfortunate, was that because they were in a different orbit, they did not dock with space station. If they had docked with the space station, could have used the robotic arm on space station and other means to inspect their vehicle to make sure there was no damage. So it was a series of bad events, bad circumstances that caused them to lose their life.
Here is Antti also. I have one question about this. So what was really the root cause? Was it so that the management or the decision makers didn't understand this in details, so they took risk without understanding what this risk meant, or how do you see?
I could spend a day, Auntie, answering this question, and there are many papers and reports, and if you go online and look at the Columbia Accident Investigation Board, CAIB has about 7 volumes, and you could look at all the different reasons why these decisions happen. But I boil it down to basically one. I list about 40 different behaviors or conditions that sociologists identify and create terms for. I boil it down to one, it's arrogance. People really didn't understand what was causing the problem, and they did not have the knowledge to be able to say whether or not that really was a problem. Yet they said they did. They said that they thought in their mind, they thought they understood the problem when they really didn't. And they went ahead and said they were safe.
May I continue? So
Absolutely.
this is very close what I have been dealing with, not with space shuttles, but I've been a quality manager for years. So I know I've spoken with top level managers, and my duty was to tell things in very simple form, or use like traffic lights, red or green, or maybe yellow, but they only accepted red or green. So was it also so that the technical staff was not able to present things clear way that the management really understood it? Or how do you see?
Yes, there were a couple of things. Number one, they used tools to try to predict what the damage was that was totally the wrong tools to use. And what they did was they took these very simplified, basically curve fits, and they created a model using these curve fits, using data that was 400 times smaller. They extrapolated 400 times data that wasn't even relevant. It was pieces of foam hitting shuttle tiles, and they were trying to extrapolate and use that information as a way to say that they understood the problem and it wasn't a problem to upper management. And upper management was not technically sharp enough to drill down to ask those tough questions. And there's a multitude of problems. What happens is the story gets diluted. The real subject matter experts aren't able to get in front of the program managers, and they don't have enough time to adequately explain to them the shortcomings of their analysis. And and so the story was mistold. It's a very similar story to the story with the Challenger accident and the O-ring. The people were using very crude, simplistic analytical models that really didn't predict and understand the real physics of the problem. They were just crude approximations. Does that help?
Yeah, thank you.
Okay. And believe me, Auntie, next time I see you, we could go into excruciating detail on this.
Yeah, we can.
But if you read the Columbia accident investigation reports, like I said, it's 7 volumes. And one of those reports, it was actually one of those volumes actually talks about the impact analysis and how little they really understood about the problem. Okay. So what I'm going to focus on now is the problem that we chose to work on, one of several, as what I call an epic challenge, was how do you fix that pizza box size hole in the wing leading edge, right? So I went back and looked at other techniques that astronauts had been training to fix a hole in the pressurized modules of space station, because I happen to be involved in this program, so I knew about this. And so when you're looking at fixing a pressurized hole in a large module, like the laboratory module, an astronaut goes outside, you basically put a mechanism that looks like this with a toggle bolt that looks like this, and you screw down a fixture, and then you inject an epoxy into that hole, and you make a nice, firm, solid repair. And so we tested that on the ground, I mean, in the neutral buoyancy lab. We tested that in the zero-G aeroplane, as you see here on the right. And so these were techniques for fixing a module. And what I'm telling the students is, once you're looking at a problem like this, and it's repairing a hole in a wing, look at any possible way you could think of to repair a hole in something you're familiar with. It could be a tire, it could be the wall of your house. In this case, we were looking at something that we knew we had designed and an astronaut would be able to operate in a space, okay? But these are the types of building block tests we would have to do eventually to ensure that it was operable, that an astronaut could go outside and actually do this in a space, okay? So this is where we got the idea for this kind of a patch that goes through, and we fill that patch with an epoxy. And I want to show some of the people that we pulled together on our team. This was a gentleman that was a material scientist at ATK Thiokol. And this was a man that really understood how to fail smart, fast, small, cheap early and often. He started looking at hundreds of different ideas for designing a plug that would survive entry heating. And so you go about using very crude techniques so that you could go through lots of different ideas, but you want to realize that the techniques you're using don't exactly simulate aerodynamic heating. You're trying to simulate the temperatures, and you're trying to make sure that this particular concept would survive the temperatures, but whether or not flow, you're not simulating the flow conditions. Could flow go underneath that patch, and will that help erode that patch? But what it does is it helps you to screen lots of different ideas. And you can do this very cheaply, very quickly. So when you look at the designs they came up with, okay, using those techniques and with very minimal analysis, they came up with these very stiff plugs made of the same material that the wing leading edge was made out of, carbon-carbon, right? But what happened was the flow is from the bottom to the top. These plugs were thick, and so you have a bump to the flow. This bevel angle was steep, so that as the flow hits that, that ramp, you get an additional heating or ramp heating. And so all these conditions, the fact that this was stiff meant that you needed over 1,300, somewhere between 1,300 and 1,800 plugs. So you had to carry a repair kit that had about 1,800 different shaped plugs in order to fit all the different curvatures of the wing leading edge, right? The other thing that the program office was looking at was how do you fix, how do you come up with a repair technique that was just a crack? So they came up with a special material that was a pre-ceramic polymer. It starts out as a polymer. It solidifies in space. It forms. It's a cracked material. It's able to flow through a gun, kind of like a caulk gun. The astronaut applies it in space. It has a whole toolkit that comes with it. But when we tested this material, right, over a small crack, the flow is from the left to the right. You see it's getting very hot. And as the material starts getting hot, even though it's forming into a ceramic material, it's becoming fluid, it's becoming viscous, and it's starting to separate and move away in the flow. And as that happens, then this crack begins to grow. This opens up, and you have a problem. So we tested lots of these ideas. The idea was, in our particular mission, this is Steve Robinson and Suichi Noguchi. We tested them on orbit, ways to fix the RCC material. We had damaged towel material in the payload bay. So this is where we're actually testing these ideas and testing the operability of these ideas in space. So here he's using a technique for basically coating the white surface of damaged tile so that it would have a high emissivity and wouldn't get too hot, but would radiate that energy to space. And it's showing you techniques for repairing it and applying it. And so what I want to show you here is that after Steve Robinson tried to create as good a repair as he possibly could on that material, on that damaged RCC material, what happened was that material expanded in orbit. What happened was it outgassed because we have a vacuum in space. So any elements of gas trapped in that material, when you put it in a vacuum, it would expand. Now, we tested this in vacuum chambers on Earth, but space is a very large vacuum. So now, let's say you repaired a wing leading edge in space and it looked like this. Would that survive entry? How do we validate that that would be good enough to survive entry, right? And we could say, yeah, we'll put the crew on the vehicle and we'll say they're okay to fly home. When we actually tested repaired leading edge specimens, this one had a circular area that was damaged, but you notice that the material that we used, that no-wax material, it was slightly too thick, right? And it cracked. And so now when we put it into the arc jet and tested it, actually a piece of this cracked material flaked off. And when that material flaked off, it caused a step to the flow, right? And that step flow caused this increased heating that you see here. And so now we think this was repaired, but we see that it actually caused additional heating and it actually caused the hole to grow. So if we would have used that material in that situation and we said it was okay, we would have potentially lost another crew. These are the things you have to think about when you're trying to investigate all your ideas. You may have been on a team that was looking at that material. You're excited. That's your idea, that crack repair material. You think that it's going to survive. You have to look at all the different ways it could fail because you could be wrong. Okay, when we saw that these teams were having problems, this is when I called together what I call a research and development team. This is when we had the Friends of Charlie come together and we used the ICE methodology and we looked at all the different ways that we could fix and we could fix a damaged leading edge. And so when I told you I want you to get together as a team and ideate, and basically you draw different sketches. You come up with multiple different ideas. You look at what happens if you have increased heating at this region. Is there a way you could design this plug so that a gap won't open up, flow will go underneath that plug and go and create a large hole. Look at multiple different ideas, right? Then you go in the laboratory and you start building these ideas. You look at all the different concepts, whether it's all the different types of materials you could use, and you start testing all these ideas simultaneously, right? Our particular concept that we came up with was a drill that you drill and tap a hole in the wing leading edge. You put a fastener in that hole, and then you basically screw down that fastener. We looked at maybe using gaskets to prevent flow from going underneath. So we looked at all these ideas simultaneously. So if we had a failure during this development phase, we had a backup. And we're going to teach you how to do that, and that's called rapid concept development. I'm just introducing these ideas. What I did was when I formed this team, I went to my friend Don Pettit's garage laboratory without anyone knowing about it. And these are just some of the different ideas that we were able to experiment with and test. And so we formed a team of people around the world, small team. They sent us our ideas. We were testing them in the laboratory in Don's garage. And why did I bring Don Pettit into this team to solve this idea? And you're going to find this out. Sometimes you're going to look at your team. You're going to realize that maybe you might need some additional help on your team. You might have to expand your team. You might need to look for subject matter experts. I brought Don into this not because he was an expert in carbon-carbon material. He was a chemist from Los Alamos National Lab, but he had this amazing ability to think creatively, to think outside the box. And we needed someone like that. So when people told us that it was impossible to drill through this material because it has a very brittle silicon carbide coating, what those people didn't do was they didn't use a punch. Basically, what we did was we basically used the spring-loaded punch and we chipped that coating. By chipping that brittle coating, we were then able to create a drill that could drill and tap precise holes through that material. And you see, we're doing this in his laboratory, right? We're doing this in his garage. And we solved the problem that teams of people at NASA and in industry failed to do. No one actually looked at actually chipping the coating before they drilled through it, okay? So we came up with a solution for drilling and tapping a hole in a wing leading edge, and we validated it. We taught astronauts how to use the power grip tool and these drill bits that we designed. They could drill and tap various size holes in the wing leading edge. And this is just a photograph of me proving that, yeah, not only could we build it, we could certify it. And I was actually able to fly it on the first mission that we flew right after the Columbia accident. So people told us this was impossible to do. And we did it in a garage. We got a patent for it. And this was another gentleman that helped us, had a company in Fort Worth, Texas, Francis Schwind. And this was one of the gentlemen that helped us build, not the drill bits, but he helped us build different fasteners made out of carbon-carbon, different patches made out of carbon-carbon. We had to come up with a way to quickly produce these patches that we could test in the laboratory. And that's what your team's going to have to do. We looked at lots of different ideas for doing this. This is a leaf spring, a multi-layer concept using a leaf spring. This is just a doubly curved shell with a gasket shown here with the yellow. And this is just a demonstration of a prototype that we developed. I want to tell the teams that are going out and doing these analyses, you have to sell your ideas to upper management, to people, that your idea is viable. The people in the program office didn't believe that our idea would work. And so what we did was we had to develop a prototype. We had a large curved section of carbon-carbon material, right? And we basically drilled and tapped a hole in it. We put in a carbon-carbon patch and a carbon-carbon fastener, and we did this right in front of their eyes. And we used the same tools that an astronaut would use if he did a spacewalk. And this just shows a demonstration of what that would look like. And this is showing how later on we handed this idea off to other teams, that basically large numbers of people now had to do the analysis to validate what the size of these patches would be, what they would look like in order to fit all the different curvatures on the wing leading edge. And so these are the different types of testing that Don Pettit and I did. We went from torch test to a very small arc jet facility that we were able to use. And once the companies realized that we could commercially fabricate this material and it could be flexible, they went out and designed their own patches. And they put large teams of people on this to actually design and validate the patches we would fly in space, and also the tools we would use, or the astronauts would use, to validate that these patches met all the specific requirements to ensure that they would survive entry heating. Okay, and this is just a demo of me in orbit, basically using the tools that an astronaut would use if they were doing a spacewalk outside the vehicle, but demonstrating how an astronaut doing an EVA would actually fix a hole in the wing leading edge. And this just shows how 8 to 10 to 18 patches would cover a large area. And this shows an example of why we need to use subject matter experts to understand this problem. The reason why the program was their patches were failing was they did not have the right analyst analyzing this problem, and they did not ask that analyst the right questions. When we put together our team, I brought my friend Pete Naffo. I asked them to analyze this problem using a code that he developed. He was an aerothermodynamicist, one of the top in the field in the world. And he basically looked at this problem, he ran his code, and in one day, he was able to determine that if we maintained this thickness of the patch to less than 1/10 of an inch, and the bevel angle of that patch to less than 6 degrees, it would not fail. And with that information going to that expert, we were able to solve that problem in a short amount of time. We were then able to design a patch that you see here, and the leading edge of that patch heats up, but it does not go above the critical temperature of the coating of the carbon-carbon material, right? And so then the other thing we did was we looked at not only small patches, but also a large flexible patch that we could carry in orbit, and we could secure with the small patches that we carry, so that we could actually fix a large pizza box size hole in the wing leading edge. And this just shows what a small team of engineers could do, like yourself, coming up with an innovative idea, taking that idea and maturing that idea to the point where we could prove that it will work, then handing it over to a much larger team, which then do all the rigorous analysis and testing to validate these systems for flight. Not only that, but some of the ideas that we had for repairing a wing, were also used and looked at by other teams that were looking at solving or repairing shuttle tile problems. What happens if you lost a large section of tile? Well, then you could use an overlay concept like this. The fasteners they would use would be different, but the mechanism for solving that problem was very similar. So that's when we validated this methodology. We proved that it works. What you're going to be experiencing is you're going to be working on these teams. We want to teach you how to work together physically as a team, but also virtually, like right now. We're in very tough times with this coronavirus. It's forcing us to work virtually. How do we do that? Luckily, we're using Valamus as a platform. We could use other techniques for talking together, using Slack, for instance. But now you have the capability to link with each other, to share ideas virtually, to connect with subject matter experts around the world to help you solve these problems. This was the beginning lecture for the ICE methodology. You're going to be going through all these different phases in detail with your instructors in Finland and in the United States. And these are some of the areas that, that you're going to be getting more and more training on. Team development, problem immersion, how do you immerse yourself in the problem? How do you share that information and learn together as a team? You're going to be learning different techniques for thinking creatively, individually, and as a team, and also techniques for working together, program management, so that you satisfy all these constraints within budget and on time. And later on during this semester, you'll be learning about rapid concept developments. Now I think we went for a really long time with me just broadcasting. And what I'd like to do is open it up. I'm going to stop sharing and I'm going to open it up for questions for our students that are online. I'm going to unmute everyone. Okay, so everyone is, I've unmuted everyone, so please be aware that you're unmuted, and so you might want to mute, or I tell you what, I'll mute everyone, and you can raise your hand and ask questions, and Anna, you could field the questions, and then that student or students will unmute their mics, and I'll answer any questions.
Sounds good. So everybody, please feel free to ask questions, raise your hand if you would like to ask something. Do we have, Charlie, any limits to what they can ask?
No limits, within reason, but no limits. Now, I don't want you to be shy. Now's the time to ask questions. The other thing we'll do, Anna, is we'll post this video to my YouTube channel for the Epic Education Foundation, and maybe we can have a blog site, or we'll post it to the platform, and the students can also ask questions. If you don't think of a question, don't have a question now, you think of one later, we can answer those questions as they come up.
I do have a question.
Okay, go ahead.
My name is Leonardo, and my question about doing those plugs in an aircraft is, in which situation an astronaut would have to go through this process of doing a plug in an aircraft? Would be something related to some hazard in space or some malfunctions in an aircraft itself?
Yeah, absolutely, Leonardo. So basically, right after the Columbia accident, as I said, our mission was the first mission right after the Columbia accident. We had this repair kit because we had time to develop this repair kit, so that now, if you could think about this, we're in orbit. The first thing we do in orbit is basically inspect the vehicle. If we see damage to the vehicle, we work with people on the ground to determine if that damage would be critical. And if it is critical, we have to then develop an emergency spacewalk, EVA, where we would have 2 astronauts go outside the vehicle, and one of them at the end of a robotic arm, and basically they would repair the vehicle, right? We then would inspect that repair, make sure it looked good, and we were given the go-ahead from the ground that we would be safe to fly home. Then we could fly that vehicle home safely, right? Let's say we had very large damage and we were using a technique like that large repair technique, and we weren't uncertain whether or not we would allow a crew to travel back with that vehicle. We had the capability to actually undock the vehicle automatically without a crew and land that vehicle safely on the ground. And so if it did survive, we would save the vehicle, right? But the crew would be left on orbit on the International Space Station, and we would launch another space shuttle with only a pilot and a commander, and we would rescue the rest of that crew and bring them home. Does that answer your question, Leonardo?
This is perfect. Thank you.
Okay.
Hey,
There was a hand raise from Christine. Do you want to go ask your question?
Hi, it's not, well, it's kind of a question. First of all, can I just say hi to my students who logged in because I see that they're on the list now. So my question to you, Charlie, this was fabulous. And even all my time working with you, I learned even more stuff on this again. So if we could share this, I would love to be able to post this with my students because we are out for 3 weeks, and it would be nice for them to have the opportunity, for those who couldn't come on today, to be able to watch this and we could have a discussion about it afterwards. So
absolutely, Christine. After, I think we give it about a day, and then it'll appear in Zoom in the videos, and then I'll download it I'll download that and then upload it to my YouTube channel, and we'll be able to, I'll give you that link, and then all the students will have it.
awesome, thank you.
Okay, then we have another hand raise from Halil. I'm sorry if I did not pronounce the name correctly. So please
Yes,
go
it's
ahead.
correct. Yes. My name is Halil. I have a question. It may kind of weird, but how did you know that when the nail got inside, it would not hurt anything behind it?
When I'm sorry, you said nail? Could you repeat
Yes.
that? I wasn't sure.
Yes.
Which nail are you talking about?
Like needle, I mean.
The needle. When it got inside, which needle?
Or maybe that's a drill bit.
Yeah, the real, I mean.
Drill bit.
Oh,
Yeah.
the drill bit, that it wouldn't
Yeah.
hurt anything inside. Well, the actual wing leading edge, Halil, it has a cavity behind it. Okay, so we know what the wing leading edge looks like in each of those components, right? So we know that when we drill through it, there's nothing behind it. There's just a large cavity.
Okay, thank you.
Okay.
hey, Charlie.
Yes.
Yeah, I want to give a shout out to my students who joined. We're also doing virtual classes, and I gave them as an assignment to watch. And I want to encourage them to speak up and ask questions. I am watching, and I'll give you credit for it.
Okay.
Charlie, this is fantastic. I've learned a lot from watching this. I've seen this presentation many times. This is your best one.
Okay. I'll make sure we capture this, Richard. And I think we have another question by Vinay.
Yeah, hi. I just had a question real quick. I noticed you mentioned you needed that spring-loaded mechanism to kind of chip into the wing leading edge, right? But why should you need that? Why can't you just use the drill bit directly to drill right in? Why do you need to chip out?
Okay, I'm gonna share my screen for 1 minute, and I'm gonna show those slides again. Okay, and I'm going to go to that slide. I'm going to answer that question, Vinay. When you look at this material, when you look at this material, Remember I told you it had a silicon carbide coating, right?
Yeah.
That silicon carbide coating, when you think about it, can everyone see it now?
Yeah.
Okay, the silicon carbide coating, Vinay, is very, very tough. If you've ever used a matter of fact, they make drill bits out of this material. It's so tough and it's so hard, if you will, right? And so when people were trying to drill through this, they looked at diamond tip drills, they looked at increasing the torque of the drills, they looked at increasing the pressure on the drills. And what they realized was they could not drill through this carbon material. It was very, very tough, very, very hard, just the nature of the material. But it's also very brittle, right? And so as we were playing around with it in the laboratory, you know, I just happened to pick up that spring-loaded center punch and hit it a couple of times. It cracked the coating. The funny thing is that when you think about it, and I'm going to stop sharing my screen so I can see again, but when you think about it, when you if you're trying to repair the wing leading edge, it would have already had some damage, right?
Yeah.
So they should have tested drill bits on damaged leading edges, but they didn't. They did not do that. And so when you think about it, astronauts to go out there, it doesn't have to be a spring-loaded drill bit. They could take a tool and they could basically just chip that coating. But the key was chipping the coating. And so when you think about these really smart PhDs in structural mechanics, material science, people that are trying to understand designing drill bits, no one thought of damaging the coating and then drilling through it. But this is where I got the idea for the Epic Challenge program. This is where I believe students in elementary school would have been hammering that thing first and trying everything possible. So a very simple idea solved that problem and opened up a whole different solution space of solutions to use to solve that problem.
Do I remember, Charlie, did you have a sample of that somewhere in your office?
I have a sample of the drill bit.
Or even the patch or
Yeah, I do. Hold on 1 minute. I'll bring it up to the camera. Okay, so this was a very complicated problem, and it had really significant constraints, and I didn't have time to go into it. But can everyone see this drill bit, right? And you see that it's stepped, so it has multiple different steps, different thicknesses. Okay. One of the reasons this was so difficult was because we had to design a drill that would drill through this material, but you couldn't push more than 5 pounds. And the reason for that is that the astronaut is in foot restraints on a flexible robotic arm. And if the astronaut pushes, the astronaut moves back away from, right? So this drill bit has to drill and has to go through the material. And so now as it's turning, it's basically grabbing onto the material and pulling the astronaut into the material, right? So it has to be able to drill through this material with less than 5 pounds, and you can't push more than 5 pounds. But once you're drilling and tapping, the tapping and screwing into the vehicle is what's keeping the astronaut connected to the specimen, right? So you could drill and tap a nice hole in this curved material, right? And then you would screw in a fastener. And so this is just showing the bottom of the fastener that we screwed in to this material. This is one of the tests we did, right? You saw Don Pettit and I with the acetylene torch, right? But we actually were able to screw that fastener in. But when you think about all the different things that I want, when I looked at this problem, I wanted to make it as simple as possible, right? So if I do not need a special screw, a special bit to drill and tap, I first wanted to look at, can I design a fastener just like you have fasteners that go in that are wood screws and metal screws that drill themselves into the material? I wanted to determine if I could design a fastener made out of carbon that I could just screw directly into the material. And it turned out we couldn't. But these are the things, because then an astronaut wouldn't have to carry this. He could just screw it directly in with a nice gun. But these are the, when I talk about multiple different ideas, test them simultaneously. The same time we're designing this, we're designing this. So if this doesn't work, I could use this. Does that make sense?
Yep.
Does that, does that?
I just had a one quick follow-up question as well. So
Yep.
So whenever you're drilling things, assuming this is in space, wouldn't the particles that come out when you're drilling, right, the part that you're drilling out, would that be any kind of worry for the astronauts? Like, couldn't they be, especially you talked about this, like the silicone material being tough, if you're drilling that out and it gets into space, especially if it's like surrounding the astronaut, is that a worry as it could puncture their spacesuit or something along those lines?
Yeah, chances are, I mean, we would look at that. Then we look at everything. For instance, any tools you take in space, right? You have to look at how sharp that tool is, whether or not it's a hazard, whether or not an astronaut could use it, because they could easily puncture their suit. And so we would think about those particles. Those particles are actually traveling at the same speed we are, right? Or very, very lower relative velocity to us, right? But you have small particles, even a chip of paint. If it's traveling in space and it's orbital debris, a small chip of paint could go through a spacesuit. It's traveling at about 7 kilometers a second, about 17,500 miles an hour. And so you're absolutely right. Those small particles could present a problem if they were traveling at high speeds. We're protected inside our suit. When we come back in, of course, we would have to inspect our suit, make sure that all that debris is off our suits. And this is also a hazard. What you're talking about is a hazard for astronauts that are going to be working and living on the moon and Mars, right? Dust is going to be a very big problem. Any other questions?
There's a Peter having a hand up.
Hi. Hello. Can you hear me?
Yes, we can hear you.
Okay, cool. So just one quick question. Let's say you doing your research process and you come up with a solution to an issue, right? How do you go about handling inefficiencies? Like, let's say you have the solution, but it's very impractical or very expensive and it's not really going to work because of that. What do you typically do in response?
Okay, that's a very good question, Peter. And so a lot of what you're seeing, that the solutions we were trying to solve, what I call epic challenges, are almost impossible. Just coming up with a solution is good enough. But as you're looking at this for future missions, or for other vehicles or for other systems, you would try to optimize this system and refine it as much as possible. Number one, so that you would conduct enough tests to convince yourself that it was going to be fail-safe, it was going to be operable, and it was going to survive. But more importantly, you try to reduce down the cost. And this is typically what happens with any new system. It could be an automobile, right? When you're designing the first airplanes, right? When you look at how that has evolved, it's almost to the point now where we're incrementally improving those ideas to eke out every ounce of efficiency we possibly can. What we're talking about in the EPIC Challenge program and in the conceptual design phase, a lot of times are looking at problems that don't even have a solution. And so first we have to understand if we can develop a solution, or we're looking for a breakthrough idea, something that's going to revolutionize a product, drive down the cost by orders of magnitude, make them easier to build, and reduce time by orders of magnitude. But you're absolutely right. As an industry develops around a particular product, you're constantly looking at eking out efficiency, making it as efficient as possible, as low cost as possible.
All right, cool. Thank you.
Okay. Let me see. I don't see any more hands up. So I think this was a success. I think we are going to stop the recording now.